Hello and welcome to today's IWCS webinar. I am now pleased to turn the webinar over to Ed Fenton, your IWCS moderator. Ed, please go ahead.
Thank you, Connie. Our IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. As Connie said, if you have questions, please use the Q&A box on the bottom right of your screen to post a question anonymously. If you wish to contact the presenter or IWCS after the presentation, you will be given the contact points at the end of the webinar. Please note that IWCS does not distribute the presentation slides from either our conference sessions or these webinars. However, please feel free to contact the presenter directly, and they will respond individually to you. Today, we welcome Charles Glew, Engineering Manager, Cable Components Group in Connecticut, USA, who will be presenting his paper on limited combustible foamable fluoropolymers for LAN cabling, enabling high operating temperatures for power over Ethernet. Charles M. Glew is the Engineering Manager at Cable Components Group, LLC, working to commercialize new and existing products from both a sales and technical perspective. Previous to this position, he was with Sabic Innovative Plastics as a member of the Commercial Development Program and Thermo Aura as the Nanowave Operations Manager. He holds a BS in Chemical Engineering and an MS in Technology Commercialization from Rensselaer Polytechnic Institute. Charles, we welcome you to present at today's IWCS webinar series event.
Good morning, everybody. Thank you, Ed, for the introduction and to IWCS for the opportunity to present. Today I'll be talking about limited combustible foamable fluoropolymers for LAN cabling, enabling operating temperatures for power over Ethernet. With this paper, we're going to look at the material properties necessary for PoE cables, specifically in the LAN market, when you have power applied to them for 0.5 amps and greater. The goal here is to use materials that can operate at elevated temperatures while achieving high electrical and fire safety performance. So we're going to start with a global vision of fire hazard assessment and looking at the two ways that materials and cables are evaluated. To start, we have the fire performance of the cable, and the goal is to look at ease of ignition, heat release, and flame propagation. And the goal of our materials here is to diminish the opportunity for the flame to ignite and to inhibit flame spread. From here, we're going to look at products of combustion, and this is classified by smoke generation, corrosivity, and toxicity. And the goal here is to enable occupants to see an escape path, to lessen the likelihood of damage to sensitive electronic equipment, and then also from a toxicity base, it has been determined from a study at the University of Pittsburgh that carbon monoxide is the greatest hazard in a fire. To start, we're going to look at the North American standard defined by the National Electric Code, and this hierarchy gets more strict for cable constructions as you go from the limited use cables, which are tested under the VW1 standards, and then as you move from general purpose to riser and to plenum cables, the test gets much more difficult to pass, and material solutions become much more important as you move up this hierarchy. So on this slide, we'll look at that hierarchy and break it up by the operating temperature of the materials in the cable construction. And then on the right-hand side, we can see which materials are chosen. So for limited use cables in VW1, you're looking at using polyolefins for insulation and polyolefins for the jacket, or very commodity PVCs. As you move up the standard, we're going to go from strictly polyolefins and PVCs to low smoke PVCs and fire retardant polyolefins. And then finally in the plenum standard, we see that we're using fluoropolymers as insulation to help pass the very strict test. What I've done on the left side is I've taken these materials and defined them by operating temperature. Now these operating temperatures are they're chosen by their ability to maintain mechanical and electrical performance. And so in the case of a plenum cable, while you have the use of fluoropolymers at a much higher operating temperatures, the introduction of a PVC is lowering the overall operating temperature of that cable. Juxtaposed to the North American standard, you have the European standard, which was required for compliance of July 1st, 2017, and this is the Construction Product Regulation Standard. Similar to the North American standard, from going to Class D to Class A, the requirements of the cable to pass the flame testing gets much more strict. As we go into the Class B2 and Class B1 arena, we see flame standards to be similar to the riser and plenum standards in the North American market. However, these have to be achieved with all non-halogenated solutions. Again, breaking down this hierarchy, we look on the right-hand side to see the materials that are used to pass these tests. Class C products are using filled low-smoke zero-halogen polyolefins as well as low-smoke zero-halogen polyolefin jackets. As we move up to the Class B2 area, we are utilizing shielding and higher filled polyolefins to pass this test. And then we have the Class B1 standard, which is very difficult to achieve because it's similar to the plenum standard in the United States, but you must use non-halogenated materials to pass this. And again, I've broken these up by operating temperature, defining them at 60 degrees C, as this is the point at which we start to see some issues with electrical and mechanical performance for polyolefins. So when applying material selection to future LAN POE applications, we look for many material properties. Because these are high-performing electrical cables, we're going to be looking at dielectric constant to be as low as possible. Limited oxygen index is key for whichever part of the hierarchy the cable is being defined under. And then the heat of combustion, so the ease of ignition. The operating temperature for which the cable can withstand, especially in POE bundles when you have heat rise at 0.5 amps or greater, and then the ease of processability. So there are many low-smoke zero-halogen polyolefins on the market that can be used to achieve higher flame performance, but due to their filling levels, they hinder processability significantly. So we have defined materials by operating temperature and dielectric constant. So on the next few slides, on the y-axis, we'll have the material property that we're looking at, and on the x-axis, we'll have dielectric constant. So as we can see here, that operating temperature for fluoropolymers is higher than most polyolefins, engineered resins, and PVCs. We're at operating temperatures around 200 degrees Celsius, all while maintaining a dielectric constant of 2.1 or less. And less than 2.1 is defined by foamed fluoropolymers. We also see that there's PEKK and PEEK, so PEEK, which have higher operating temperatures. However, their dielectric performance is not as good as fluoropolymers, and this could be a hindrance in higher speed communications cables, specifically the Category 6A space. Again, we are looking at a material property heat release against dielectric constant. We show that the fluoropolymers have heat release of less than 3,500 BTUs per pound, and again maintaining that dielectric of 2.1 and less than 2.1 when we are foaming it at 35%. We do see that we have polyolefins around the dielectric of 2.1, but their heat release is similar to that of petrochemicals. And finally, we'll be looking at limited oxygen index by dielectric constant. This is a really significant slide. It really shows how fluoropolymers operate compared to other polymers. They have limited oxygen index of 90%, and all still while maintaining that 2.1 dielectric constant. PVDF, which you see here, is also a fluoropolymer, has a limited oxygen index of around 60 degrees C, but the dielectric goes all the way to 5.7. So having defined these material properties, we can see that for fluoropolymers, FEP, MFA, and PFA, as well as their foamed counterparts, that we really have a confluence of material properties where we're maintaining an operating temperature greater than 150 degrees C, a limited oxygen index greater than 90%, and heat release of less than 3,000 BTUs. And the significant point here is that all of these properties are achieved while maintaining a dielectric constant less than 2.2. So when looking at these materials for selection in power over Ethernet cables, one of the properties that we wanted to pinpoint was how does the application of power to power over Ethernet cables affect heat rise within the 192 cable bundle. So what cable components did is we made an apparatus at our facility where we put thermocouples between the jacket and the insulation of category 6E and 6A cables, and then we put these thermocouples throughout the concentric rings of the cable bundle, starting at the center and all the way to the outside. And then we applied amperages from 0.1 to 1 amp, and we studied the heat rise in the cable bundle. We also looked at these cable bundles across a variety of gauge sizes, of copper wire gauge sizes, looking at 22, 23, and 24 gauge wire. So what we found was that, and this is looking at 23 gauge wire here, is that above 0.5 amps, heat rise in the interior of the cable bundle was significant. We saw it approaching 100 degrees C in temperature rise very quickly, and that at 0.5 amps was about the threshold when we started to see heat rise above 60 degrees C. And this is significant because, as we defined earlier, polyolefin-based materials, their operating temperature for maintaining their mechanical and electrical performance is around 60 degrees C. So we see that we're going above the characteristics of polyolefins and needing material solutions to meet 0.5 amps and greater in power over Ethernet cables. And again, to reiterate, we're looking at, on the left-hand side, heat rise for 23 gauge copper, and we see that at 0.8 amps and then up to 1 amp, we have 150 degrees C temperature change, so the temperature at the interior of the cable bundle was around 200 degrees C. We've then broken down heat rise by amperage rating, and on the x-axis in this right-hand chart, you'll see the material selection to achieve the operating temperature at that amperage. So we see that quickly at 0.6 amps in the orange box, we're quickly moving into semi-crystalline fluoropolymers and fully fluorinated polymers for amperage of greater than 0.6. So PVDF is a material choice for 150 degrees C, FEP, MFA, and PFA for 200 degrees C and greater, and these would be for cables using 0.9 amps or more. One of the things of interest to us was to look at using foamable fluoropolymers versus solid fluoropolymers in these cable bundles. And we found that there was less heat rise at the interior of the cable bundle when we used foamed fluoropolymers. So at 0.5 amps of power, we saw that there was a 9 degrees F difference in heat rise, or 5 degrees C cooler in the interior of the cable bundle. And then at 1 amp, we saw the interior of the cable bundle was 18 degrees Fahrenheit cooler, or 10 degrees C cooler in the interior of the cable bundle. So here we're looking at heat rise across wire gauge sizes. At the top we have 22 gauge wire, and at the bottom we have 24 gauge wire. As size of the wire decreases, we see heat rise in the interior of the cable increasing. And of note here, we have 24 gauge wire in a 192 cable bundle, and at 1 amp we saw a Tmax value of 63 degrees C. So looking at slides earlier, PFA is one of the only options to withstand the operating temperature at 0.1 amps with 24 gauge wire. Then we see a 23 gauge wire, we have 219 degrees C Tmax, and then again 22 gauge wire, 183 degrees C Tmax. So one of the things that we also wanted to couple this presentation was an understanding of how large Power over Ethernet and the Internet of Things will be in the future. This is just looking at the Chinese construction market. I mean, it's growing at 6% of GDP, and it has been that for many years and looks like it will continue. And just some of the statistics is that 221 cities in China will have 1 million residents by 2025. And due to the urbanization of China, this is a great area for Power over Ethernet, because as they build more buildings and they urbanize as a population, the ability to provide both power and communication cable either to a wireless access point, to a desk for a computer, even very large area of growth would be lighting. We can really see that there's an avenue for PoE. And as more things are connected and more urbanization occurs, we'll see PoE cables that have a higher and higher amperages ratings to serve more products. So again, this is just looking at the growth for the Internet of Things in PoE. We see that by 2022, there will be a 90% increase of cables with PoE to the desk, so you'll both use your Ethernet port to charge your computer and have communication. We see by 2022, wireless access points, 80% of them using Power over Ethernet cords, and then also the red line there, a significant increase in the amount of LED lights using Power over Ethernet. And this is a game changer for smart lighting, because you can get both the communication and data to the light. So this is a product that CCG works on, which is fluorofoamed. It's a foamed fluoropolymer, and we've seen significant, a significant avenue for fluorofoam within the PoE space due to its ability to take the operating temperature of 0.5 and amp greater PoE cables. So one such construction for 0.5 amps and 24 gauge wire. I apologize, on this slide this should be referring to a Category 6A cable, not a Category 6 cable, but we see fluorofoam insulation, crossweb, and then a PVC jacket to withstand 0.5 amps. And this would maintain the electrical performance and the mechanical integrity of the cable at these elevated operating temperatures. And then as operating temperature elevates further with a 1 amp solution, we're looking at a totally foamed fluoropolymer solution where we have a foamed fluoropolymer jacket, a foamed fluoropolymer insulation, and a foamed fluoropolymer crossweb, all while maintaining, again, the electrical performance and the mechanical performance of the cable in the interior of the bundle, and while seeing 1 amp of power. So, in conclusion, a more connected world means that there's going to be more cabling infrastructure, as we saw with the urbanization of China. With that, space to run both power and communications wire is going to become more and more congested, so there'll be the need to have power and data over the same cable. And that with these cables, above 0.5 amps of power, we see heat rise of greater than 100 degrees C, and with that said, we'll need materials to match that. So for these materials to maintain electrical, thermal, and mechanical integrity, FEP, MFA, and PFA, as well as their foamed counterparts, have the appropriate balance of properties to enable this. And, moving forward, especially in China, due to these material needs, it's key that we develop wire and cable standards that reflect the material demands of future applications. So that'll be it. Thank you, everybody.
And thank you, Charles. At this time, we will ask as many questions from the attendees as time permits, starting with this first question. For potential halogen-free cable solutions, do you see PEKK or any other materials with the potential of meeting the balance of transmission, temperature, fire performance, and heat release in the Cat 6 or higher solutions?
There's definitely a space for them. This is a great opportunity to foam an engineered resin to help with its electrical properties. But in an insulation application, it may not be as good, but maybe in a jacketing application, we can see the use of engineered resins to help increase operating temperature in a non-halogenated solution. The issue will be is just overcoming the increased dielectric constant of these materials when trying to get to high-end Category 6A cables.
Okay, thank you. Next, will foamed materials in each component of the data cable still meet the physical requirements as established by standards such as UL 444 or IEC equivalents?
Yes, and this is all due to how the cell structure is made up within the cable, and that's where we do a lot of work at Cable Components Group. By decreasing the cell size and making sure you have the best cell dispersion within these components, you're able to maintain mechanical integrity throughout the insulation, the cross filler, and the jacket.
Thank you. Next, with the differences between the requirements in Europe, CPR, North America, NEC and CEC, and in China and Asia, will powering of devices over data cables become the driving force in harmonizing data cable solutions around the world?
I would hope so, because we see that power over Ethernet is so important to the future of communications cables, especially with the urbanization of the world, and we really need material solutions that will enable this. Because of that, you have a CPR standard which is completely non-halogenated, and a North American standard which allows for halogenated materials. And I would hope that we can find a way to use the materials that enable a harmonized standard.
Okay, thank you. Next, can you explain why the foam insulation can decrease the heat generation?
So we have to look more into this at Cable Components Group, but one of our theories is that there's less mass to the cable, so less amount of polymer to retain the heat, so almost decreasing the thermal mass of the cable bundle is helping to decrease the overall temperature within it.
Okay, thank you. What level of foaming did you attain in the FEP?
All of this was done at 35 to 40% foam.
Thank you. Is there a difference in, quote, normal conditions, unquote, on electrical properties between Cat 6 in foamed polyethylene and foamed FEP?
If I understand this correctly, the question is asking, are there a difference in electrical performance between foamed polyethylene and foamed FEP?
Yes, in Cat 6, yes.
So this is an interesting question. So if we're talking about room temperature, they have very similar electrical performance. You have a dielectric constant of 2.1, and when you're foaming these, you see a linear decline in dielectric constant. So at 30% foam in both materials, you're achieving around a 1.8 dielectric constant. However, as you increase temperature, Alistair Duffy's group at DeMont University has done work that shows that the electrical properties of polyolefins degrade as they're thermally cycled above 60 degrees C. And this is where we see FEP having a significant impact for POE someday, because we want to study its ability to maintain its electrical performance at elevated temperatures.
Okay, thank you. Next, the values provided for dielectric constant are given at what frequency?
I will have to follow up on that one and look back at our testing procedure.
Okay, good. Next, when using a foamed FEP, is it beneficial to add an outside skin covering the foam material?
This is a unique case here. Specifically, fluorofoam, which we used to do this testing, is a self-skinning material, so there's no need to add a skinning extruder to the insulation process.
Okay. And at this point, Charles, I'm seeing no further questions.
Okay.
So I would like to thank you for presenting this very interesting and important topic today. Please note the contact points being shown here should you wish to contact Charles after today's event. Each of these IWCS webinar series presentation events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 a.m. Eastern USA time. Our next scheduled webinar event will be on Friday, November 16th at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event a few weeks prior. Please feel free to share our announcements with your colleagues so that they can join and register as well. For over 66 years, the IWCS International Cable and Connectivity Symposium has been the recognized leader showcasing new technologies in cable and connectivity products, processes, and applications. Our next annual conference will take place on Sunday, September 29th through Wednesday, October 2nd, 2019 at the Charlotte Convention Center in Charlotte, North Carolina, USA. In addition, the third annual UL and IWCS China Cable and Connectivity Symposium will take place on Monday, March 25th through Wednesday, March 27th, 2019 at the Marriott Hotel City Center in Shanghai, China. Please visit our website at iwcs.org for more event details. In just a moment, you will see a brief survey so that you can provide us your feedback and comments on today's event so that we can further improve this webinar series for you. Thank you for participating, and this concludes today's event.